Let's consider the effects of having a different Ka value on a weak acid in a titration, and also the effect of having low concentrations. So working through this one, you can see that just using one of the figures in the book, if we're using a strong acid, and notice here's our experimental conditions. Our base that we're titrating with is at 100 millimolar, 0.1 molar, and then our strong acid is going to be at 20 millimolar, 0.020 molar, and we're going to have 50 milliliters of it. And so you can see that that means we're going to need 10 milliliters of our really strong one to get to our equivalence point. We see that two different ways. We can just look at the mole ratios here, and it'll jump out at us. This is 5 times less concentrated, and so it takes 5 times less volume to get there. All right, so we see what would happen with the strong acid. Remember, strong acids, we're typically saying their pKa's are going to be much less than 2, and often are going to be 0 or possibly even a negative number depending on how tricky they got in their measurement. We typically don't talk about pKa at all for a strong acid. We just flat out say strong acid, 100% dissociated in water. Now you say to yourself, well, okay, why do I end up having this exact pH? Well, remember, we just go ahead and we use our pH equation. We calculate it based off of how much H plus or OH minus is present in our solution. We see that we've got those numbers right over here. So if we calculate moles, or actually plug in our molarity into negative log of concentration of H plus, we'd be getting our pH, and we see that our pH starts rising as our OH minus takes away the dissolved acid, and eventually we hit neutralization, and we end up having that rising moment be right here centered at 7, which is not surprising to us since pH of 7 is going to be our totally neutral solution, and that's right where our equivalence point should be. Now, things end up being a bit more complicated when we start talking about things that are actually weak acids. Now you see here we have a pKa of 2, 4, 6, 8, or 10 drawn in. And let's highlight a few key points. Now, just think through what's going to be happening as we add a strong base to this. If we get halfway through the titration to our equivalence point, we've seen this before probably, right here in the middle, we're finally going to reach the moment where we've got the same amount of strong acid and the conjugate base, weak acid and the conjugate base present in the solution. When we have that, we plug it into Henderson-Hasselbalch, pKa plus log A minus over HA. I'll leave off the brackets both for clarity and also because we could be in molarity or in moles, and either way would still work out. And we've seen that in separate pieces of this whole process. When these are at the same concentration, in other words, halfway along your titration, log of 1 equals 0, and so we have pH equals pKa. Now right there we'd expect that pH equals pKa, but it's saying pKa is 2, and we're seeing that it's actually just a bit above that. It's more like 2.5 for this acid. It's just that when we're at really acidic pKa's, we actually have to start considering that we're reaching the leveling effect of water. And so properly speaking, at really strong acids, concentrated acid solutions or really acidic conditions with small pKa's, we have to start being concerned about what's happening with the leveling effect in water, which means it's time for systematic treatment of equilibrium if we're calculating these points in the intermediate range at high accuracy. Now when we get up to pK of 4, you can see that we've kind of got away from that issue. We're here at the center of our titration curve, so half of our equivalence volume, and pK equals pH, just like we expect. Same thing for each of these other ones. We're centered right there. And when we look at what's happening over here, we can just see that it has our rising moment. Now, if we were to go to pKa's above 10, notice how flat it's starting to get here. It's really difficult to spot the rising spot, and that's just because right now we're so basic, the leveling effect of water is having an effect once again. So you can see that we're definitely good doing our titrations in this whole range, probably even out to 9 and down to 3. But going below that, we aren't going to be able to find a whole lot about pKa anymore. If we're at least titrating in the right direction, we'll be able to get quantitation very easily. So here, very easy to get quantitation for a strong acid. Very difficult to get quantitation for a reasonable base titrating with a base. So obviously here we'd have to actually swap We'd actually set up our basic weak acid and use HCl as our titrant, and we'd titrate the other direction. Then we'd be able to spot that equivalence point much more easily. Now let's think through what's going to happen as we get more and more dilute. Now notice that over here we are at 20 millimoles, 20 millimolar, and that's where we're starting out with this one, 20 millimolar. And on this side our pKa is going to be 5, but we're going to be using the same concentration of our acid to start with, and then going more and more dilute. Now to make sure that our equivalence point still matches up, and so we can actually have a direct comparison of these, what they did taking these plots, they diluted the sodium hydroxide each time so that it stayed 5 times greater than the concentration of our acid. So same ratio of conditions as we had over here, but we do have a different set of pHs. And like we said, that's just so our endpoint stays locked in. Now notice, our, I don't want to say stronger, our more concentrated solution behaves just like we'd expect it to, and has a very nice sharp rise. But as we get more and more dilute, the rise gets a lot less clear. We have a bit more of a slope in that area. It's going to be harder to spot our exact equivalence volumes, especially when you put in experimental noise on top of this. And when you get more and more dilute, eventually, just like we've seen before, if you have a dilute enough solution, so if you have, let's just say, 10 to the minus 8 molar of your acid, it's not going to be a pH of 8. It's going to be a pH of about 7, because you've got dilute enough now that you have to focus on the autoionization of water. And we've seen that in the workshops where we say, yep, in really acidic conditions, we have to worry about activity. In really dilute conditions, we have to start caring about using our systematic treatment of equilibrium. And then there's that sweet spot in between, and we know that this was definitely in that sweet spot. Even the 2 millimolar was still okay. Once we start getting into the decimals of millimolars, we're starting to get pretty dilute, and so we start seeing a lot of those features kind of wash out, because most of what we're seeing is centering right here at pH of 7 for water. Water's having the really big effect at that point, and so you see these really dilute solutions. That's exactly where we see things end up. So we want to make sure that we don't end up too dilute when we're doing our titrations if we can help it. And if we can't help it, we need to get pretty tricky experimentally.